Alright, so we're going to talk about clustering, in particular K-means clustering, because it fits more neatly into the narrative of this course, particularly empirical risk minimization. So, first of all, throughout this course we've been talking about supervised learning, right? And of course in supervised learning, the basic idea was that our yi labels were given to us at some point, right? And this is our response, right? And we thought of it as these yi's are sort of supervising the learning in some sense. Now the unsupervised learning, so unsupervised, here the basic idea is that there's no response variable, so there's no yi's. That's the big feature about it, it's just not supervised. And so typically we think of a couple of different scenarios where we would be in this setting, but they're certainly not the only scenarios where you would not have a supervising variable. So for example, an unsupervised setting is clustering, where you're tasked with grouping samples. So you have X samples and you're tasked with grouping X samples together in some way called clustering them. And then another example is dimension reduction, where you're trying to reduce a large high-dimensional vectors, a bunch of samples of that, to something that's much more low-dimensional, that's sort of representative. But there's other things like image segmentation and so on. So this is by no means an exhaustive list, but I did want to show a few things, a few instances where a lot of what we've talked about in this class so far also applies to the unsupervised setting. So let's first, what are going to be the challenges that we can anticipate? So let's first note that in the supervised setting, the yi's were used, right? So these yi's were used in the loss, right? And that sort of guided our prediction. So we have to come up with losses, if we are going to use the empirical risk minimization framework, that don't require a supervising variable. And then when we tested, right, we tested and selected a model. So for model selection, and so we'll call that tuning, testing and tuning, we also saw that the yi's were extremely useful. And we're going to have to come up with completely different alternatives for that in these settings. And then we also have the ROC and the PR curves were an example of ways of testing. And the final testing and evaluating the performance of our method. Okay, so in the unsupervised setting, now we don't have these yi's, so our data just consists of the xi's, right? I going from 1 to n. Okay, and then of course we're going to assume that our xi lies within our p. So the p-dimensional vectors. And this is the data. Okay, so here we are, and our task in the clustering, so task for clustering, is to learn some cluster assignment. So we're just going to call these some latent variables, zi, and zi is going to be within 1 up to capital K, right? Where this is the number of clusters. And we're going to assume for now that we just have some fixed number of clusters in mind. And the zi's are our cluster assignments. So if zi is equal to j, then that indicates that the ith sample, we're assigning it to the jth cluster. Okay, and now let's think about an example of this. So, for example, if we have several different data points, we have clusters C1, which is equal to, for example, X1, X3, and X7. That's one example. We have C2, which is equal to x2, x5, and x6. And C3, which is equal to x4, x8, and x9. x8 and x9. So these are different vectors, and somehow they're similar enough for us to cluster them together within the clusters, and dissimilar enough between the clusters for us not to cluster them together. And then Zi is going to be equal to 1 because the first sample is within the first cluster. Z2 is equal to 1, or sorry, Z3 is equal to 1, and Z7 is equal to 1, while Z2 is equal to 2, and so on, and Z4 is equal to 3, and so on. Okay, so that's just our cluster assignments, and this is one of the things, this is our primary goal, is learning them, but then another thing that we would like to learn are cluster centers. So we want to also learn cluster centers, and these would be M sub k, which is, we think of them as representatives, so they're also in RP, they're the same space as the data, representatives of the data, and these are cluster centers. And this is for little k going from 1 up to big K. Okay. So there's one interpretation of this which I think is pretty instructive, and it's the compression interpretation. So the compression interpretation says let's summarize our data. With only the cluster assignments. So this is with only our cluster assignments, which are our zi's, I going from 1 to n, and then also the cluster centers, m sub k, k going from 1 to capital K. So the basic idea is that you can somehow compress your data from n p-dimensional vectors to n cluster assignments, which are just very small integers, and then the cluster centers, m sub k, which there's only capital K of them. So you've significantly reduced the size of your data by going effectively from n p-dimensional floats, vector of floats, to n different integers, a very small size. So that's one interpretation. That's one sort of guiding principle. We're going to think of this as a way of, this is one interpretation. There's other reasons why we would want to cluster. So another reason is for exploratory data analysis, and I would say this is the most common interpretation or use of clustering. Exploratory data analysis. So in this setting, our cluster assignments sort of mean something, right? So that these are, they mean something. And they either mean something about the distribution of the data or about the data points themselves. One thing you can think about is in clustering, the cluster centers can serve as sort of representatives of the cluster themselves, and so you're in some sense prototyping your data by saying there's k different data points, or hallucinated data points, which serve as prototypes for your data. Right? Now, you could also think about clustering as having some downstream application in a data processing pipeline. And so, for example, this could be in a semi-supervised setting, where the clusters themselves form features for supervised learning. Okay, so that's sometimes that's pretty common, or it could be used as an initial feature selection. In some application, that's done, and of course, the reason you might want to do this is because clusters can, when used in, for example, linear regression or linear classifiers, that could give you a nonlinear method in the end, because the clustering itself, the indicator of the cluster, is nonlinear in X. It has a discontinuity, in fact. So, those are various different reasons why you might want to use clustering, but the most common one is for exploratory data analysis and prototyping. Okay, so what is K-means clustering? So K-means is a principle for clustering, which is really inspired by this data compression idea. And so let's think about this for a second. If so, let's do the K-means algorithm. If I gave you the both the zi's and the m sub k's, right? If I gave you those, which these are the cluster assignments and the cluster centers respectively, then how would you come up with some reconstruction of xi? Right? Well, I would say because m sub k is supposed to be a representative for the cluster, and it's in RP, right? It's a p-dimensional vector. Then xi is hopefully well approximated by m sub k, where k is equal to zi, right? And so this leads to an approximation of xi as m sub zi. So that's one thing. And if we're going to make that approximation, then what is going to be our measure of loss, right? Because we want to use some loss minimization framework to do K-means. So the basic idea is that if we're going to try to approximate xi with m sub zi, then we could use any of our favorite losses for vectors, right? And so, for example, we could use Euclidean distance. So let's suppose that we're going to do that. So our objective is going to be the sum from I going from 1 to n. Let's divide by n, just for fun, of xi minus m sub zi. And if we're using Euclidean distance, then it's just the 2 norms squared, and we square this. So sometimes this inner part is called the distortion. Sometimes that's called the distortion. And let's just write it as j sub z m. Right? Now, what we want to do, we want to minimize with respect to the selection of zi's, going from 1 to n, and m sub k, k going from 1 to capital K. Right? We want to minimize j sub z m. Okay, all well and good. And so let's think about this distortion for a minute. Right? We have this square 2 norm loss. This, of course, this 2 norm squared is just the sum of the squared differences between the components, Zij and Mzij. And so we can draw what this distortion means for clustering. So let's choose a color for the data points, which will just be black. So this is our data, for example. Okay. Now our clusters are going to be, so we'll mark the boundaries of our clusters in red. Suppose that our cluster 1 is everything within this circle, within this, and then cluster 2 is everything in that shape, and then cluster 3 is everything in this shape. Okay. Now suppose that we need to find, or need to select, for example, a reasonable cluster center, then it might land here. It might, for cluster 1, so this is C1, this is cluster 1, and this is M sub 1. It might land here, for example, M sub 2 for cluster 2, and it might land here, M sub 3 for cluster 3. Okay. So this would be a reasonable clustering. Everything within here, everything within one of these would have Zi equal to 1. Everything within here would have Zi equal to 2. And everything within cluster 3 would have Zi equal to 3. Right. Okay, so let's just notice that J sub Zm, that this is equal to also 1 over n, the sum of little k going from 1 to capital K, sum of over I such that Zi is equal to little k of the xi minus m sub k, 2 norm squared, right? So the basic idea is that if I want to sum over all I, well, I could break them into the estimated clusters, the Zi's, and then this is a within cluster distortion. This portion is a within cluster distortion. So, let's think about this. If we were to fix the cluster assignments, so for fixed Zi's, we are going to be, we could think about minimizing subject to the selection of m sub k, j of z m. We could think about doing this. And this would give us that the m hat sub k is equal to this average over the size of cluster k of the elements I in ck of xi. So if we just fix the zi's, then we're just asking what is going to be the minimizer of this square error loss, right? And we know that the average is the minimizer of a square error loss, right? And that holds for each dimension. And so we're just going to average each of the dimensions of the xi's independently, separately, for all elements of the cluster. Right? So let's also think about what we could do if we were to, say, fix the m sub k now. So suppose we knew what the true m sub k was, or suppose, well, maybe there isn't a true m sub k, but suppose that we have some choice of m sub k. And if we want to minimize subject to minimize over the zi's of this j sub z m, then let's think about this. If you had said, if you told me that these three are going to be the cluster centers, and I had to choose which cluster a new element belongs to, say this one here, then I would just look to see which of these cluster centers is the closest to this element. Because if I were to choose one of the cluster, like say C2 instead of C1, when M2 is further from this point than M1, then that's only going to increase the distortion. You can just make that argument, make the substitution of M1 for M2 when you're evaluating the square error loss. You'll find that you'll get just a worse distortion by assigning it to C2 over C1. So in this case, we are going to just select the Zi that has the closest cluster center. So Zi is equal to the argmin of the 2 norm between xi and m sub k. Right. And this is the argmin over k. So this begs for us to make an algorithm, right? Which would be, let's put a hat over that. This begs for us to make an algorithm out of this, and this is called Lloyd's algorithm. So Lloyd's algorithm, it's really just an alternating minimization scheme. So we talked about a lot of optimization methods here. One of them is called alternating minimization, where we fix one of the elements of an objective, so the z's, and then we minimize the objective with respect to m, and then we alternate. We fix the solution with respect, we fix m, and then minimize with respect to z. Right? Okay. So this is really just alternating minimization, or coordinate descent is another name for that. And so first of all, we have to initialize m sub k. And we typically do this randomly. Sometimes they call this Kmeans plus plus. So once we have random initializations of the m sub k, then let's just alternate. So 2, alternate between the following update steps. A is update Zi, which gets the argmin over k of xi minus m sub k, 2 norm squared. Right? Then we do this for all I. And then B, we're going to update m sub k. We're going to update this with the 1 over size of c sub k of the sum I going from 1 to, this is I such that Zi is equal to k of xi. So this is just the average of the elements within the cluster. And then this is, of course, where c sub k is equal to the I, such that Zi is equal to k. So we could have just written this as I within c sub k. That's another way to write it. Okay, so when we make that update, we're just alternating these. And one thing you can see is that J, the subjective, is non-increasing in its iterations. So let's think about that for a minute. How could you, well, because when we fix the Zi, we're selecting the m hat k's that are going to be the minimizers of J, right? So fixing Zi, you already had an m sub k, right? You already had a valid m sub k. And so when you choose the m sub k that minimizes J, subject to the Z being fixed, then you're only going to decrease the objective. And similarly, for when you fix m sub k, the second step of the alternation, then minimizing with respect to Z, it's only going to decrease the objective, right? And so that means that J is increasing in its iterations. Hence, J is non-increasing. Okay, great. Now, in the iterations, so during Floyd's algorithm. Now, another thing that we know about this is that there are only a finite number of possible configurations, right? Because the zi's are discrete. Now, there's a lot of them, but there's only a finite number of them. So there's a finite number okay? Therefore, based on these two things, the algorithm will actually terminate. So eventually it'll stop updating. Okay? So, I think this is instructive because if you find that a lot of times in these update rules, we don't, it's not always clear what a good stopping criteria is. But in the case of Floyd's algorithm, we don't really have to put up a stopping criteria just if the update stops or if the objective ceases to be decreased. So there's some pedagogical cases where you could make changes to the algorithm, or to the you could come up with some pedagogical data sets where any change to the zi's or some changes to the zi's will keep the objective the same, but those changes would be legitimate changes. That's possible. But in that case, you might not. In that case, you could always just check to see if the J is decreasing, and as soon as it ceases to decrease, then you can terminate the algorithm. Right. So that's Lloyd's algorithm. We know that it terminates, so you just stop when J ceases to decrease. So as an exercise, I think this could be instructive. As an exercise, 10.1, I would encourage you to do the following thing. Just try to come up with some silly example, some simple example. An example of just a toy data, a small data set. And I'll even tell you what you should do. You should have n be 4 and p be 2. So make it two-dimensional and 4 data points, such that, such that Lloyd's algorithm terminates at a suboptimal spot, right? So you can choose where it starts. So we'll just say it is stuck at a suboptimal solution. So assignment. Okay? And think about the situations where we're just in 2 dimensions and n equals 4. Just try to draw a picture and think about what the clusters are for that picture. So I'll come back in the next video and answer this question, and then we'll talk about dimension reduction. But before actually I finish with this video, I would like to mention one thing. So this J, ZM, let's go at the very beginning when we talk about Kmeans algorithm. The objective looks like the average of losses, right? So it is like an empirical risk minimization in that respect. like it's the average of losses. And we could, for example, try to do some sort of a stochastic version of this algorithm, right? We could make updates just based on a mini batch, for example. Now, it might not work very well, and it wouldn't be the K-means algorithm as Lloyd laid it out, but there is one major difference with unsupervised learning, is that you can't then expect that your test loss is going to give you a good way of tuning the parameter capital K. So typically we think of capital K as just some number that's given to you based off of context. For exploratory data analysis, maybe you would select it to be a reasonable number. For compression, maybe you would base K based on the amount of bytes that are required to represent the data at the end, and so on. But you cannot use the test error to select K. You should convince yourself that the test error is always going to prefer higher K. Right? So you can convince yourself of that. And so that's what you find. And there are some methods that we don't have time to go through in this course, but there are some algorithms, some of them heuristic, for selecting K in K-means. So I just wanted to make that point. So this is a major departure from supervised learning in the empirical risk minimization framework. Okay, so try to figure out some way to make Lloyd's algorithm get stuck.